Hi everyone. Today I'm going to talk about the origins of, or at least some motivations for the DQN algorithm in reinforcement learning. So DQN stands for Deep Q Network. And today I want to give you a very small gist of why such an algorithm was developed and executed about 10 years ago and had an amazing impact on the field of reinforcement learning. So to set some context, there's this algorithm called tabular queue learning that some of you may be aware of, which is an approach to solve reinforcement learning problems. Which let me start with what is reinforcement learning. It's the problem of sequential decision making when you don't know much about your environment. So you have to do trial and error, which basically corresponds to exploration and exploitation, while understanding that your actions may have long-term consequences. Okay, that's the one of the aspects that gives this problem family a little bit more generality than problems like contextual awareness. Okay, so what is tabular queue learning, which is a more traditional algorithm, which inspires actually how DQN works as well, is as follows. So in tabular queue learning, the agent who needs to take actions in the environment gets a state observation and a reward observation from previous interaction. And based on that, at any given step, they need to take an action. And once they take an action, the environment responds back with the next state and the next reward. And this continuously, this interactive loop continues on and on, okay, till some termination condition happens. So what does the agent do? The agent maintains a table of Q values. So what are Q values? Q values are state action values, which basically assign a number to a state and action pair. Okay, so what do I mean by that? So think of a environment which has 10 states. Okay, there are only 10 possible situations or scenarios that are possible in this environment. And for those, each of the 10 states, you could potentially take 4 actions. Let's say you're a robot, you're going north, west, east, south, and 10 states correspond to, let's say, a 5x2 grid. Okay, so a table in tabular queue learning corresponds to maintaining this Q value table. Okay, so every row, for example, corresponds to a state, and there are only 2 columns, so 2 columns correspond to the two. Sorry, the two. Or if you have 4 actions, let's say, then the 4 columns correspond to the 4 actions you can take. Okay, so what do we do in Q learning is just update the entries of this table. Okay, so this table, the matrix, whatever you want to call it, we're going to update it. And how we're going to do that is we just need to do 2 things. First is pick an action to take at a given state. And once we observe the next state and reward, we can update an entry in this table. Okay, so how do we pick an action? As I said, there has to be trial and error. So with some probability, we'll take a random action. And with some other probability, we'll take an action which is which has the highest number in that state, in that row. For example, in a particular state row, there are going to be 4 numbers for each of the 4 actions, right, in that table. So one of those numbers is going to be the highest, and the action corresponding to that is what we're going to play. Okay, and once we play or act out that action, we're going to get a reward at the next state. And based on these 4 observations, so current state, what action I took, what's the next state I reached, and what's the reward I got, I'm going to make an update to this table. And I'm going to keep repeating this on and on. And some researchers have shown that this process actually works out really well in the sense that then the agent learns to be learns to take actions which are actually not myopic, as in they can take into account what's going to happen in the future a little bit, and overall you can actually maximize your reward collection. Okay, maximize the expected rewards you get. Okay. So this is a tabular queue learning, but shortfall. So it has a shortfall, which is that it cannot really scale. Okay, beyond the like a 10 state or 4 action situation. If you have a million states and let's say 40 actions, you have 40 million entries that you need to update, and so it's not really scalable. And so the unique insight which kind of motivates towards DQN and other things is that, okay, it's a function of 2 inputs, state and action. So think of state representation and action representations to vectors. Then you're basically saying, hey, I input 2 vectors, I need to produce a number, right? So it's like a regression type of function. And so I can just approximate it using a function family. And instead of now updating a cell entry in a table, I'm going to update the parameters of a function. It could be a linear function, it could be a decision tree. And in DQN, when it was implemented 10 years ago on Atari environment, it happened to be a CNN because the environment had games, and so you had game screens as input to this function, and then you would produce Q values, okay, for every action that you could take on using your joystick. So that's the first thing. So you have, instead of updating entries of a table, you're updating parameters of a neural network. Okay. Now, to update parameters of a neural network, we know we want to update it, and let's say we want to use gradient descent technique. What will we need? We need now what is the data and what's the objective function, right? And what is the neural network? The neural network is the Q function. Okay. The objective happens to be inspired by, or actually, there's a lot of obviously formal ways to define this, but it's basically inspired by what is called temporal difference error, where you're trying to minimize the Q value versus the reward plus a discounted future Q value. Okay, so it just turns out that if you had actually learned really good Q values, as in the optimal Q values, then there should be zero temporal difference error, that your current optimal Q value is exactly equal to the next reward you get plus a discounted value or discounted expected value of the future Q value at some new state and action and so on. Okay, so because there's a nice interpretation, we can then therefore minimize this temporal difference error. And to do that, so we can minimize that by minimizing square difference of the temporal difference error, and that kind of naturally gives rise to some sort of regression type of a problem here. Okay. And the second thing is, to do this, we need some data. And in reinforcement learning, the data is actually non-IID. So in order to tackle that, the researchers proposed what is called a replay buffer or experience replay buffer, where you collect data, you're decoupling the update step with the collection, acting in the environment step. So you keep acting in the environment, you get to new states, you take actions, you get rewards, you get to the next states, and so on. You collect the data, those 4 tuples, and when you want to do this update of the parameters of the network, you subsample a random batch, okay, from this replay buffer, basically a database, so that you kind of decouple, you kind of minimize the dependency. You're not picking the next immediate successive rows in this data set, right? And so that's experience replay. So you subsample a batch, and then you do this squared loss minimization. The second thing is also that in this temporal difference error, I didn't mention it earlier, but the target, which is let's say the future reward plus next reward plus a discounted future Q value, that also has the parameters. For example, the parameters of CNN, and the function you're approximating, the Q function, also has the parameters. So it's not exactly like a regression objective. And so what we do is in the targets, when we are using the future Q value, where there are parameters, those parameters will call them as fixed, or will make them fixed or frozen for a period of time and periodically update them. So that in effect, our problem really looks like a regression problem where we are updating the parameters of the Q function to match these some regression targets, so the fixed targets, fixed numbers that we want to kind of approximate. Okay, so with these 2 fixes, experience replay and freezing of targets, this algorithm is shown to be stable and works really well compared to humans, as well as linear approximations for these 50 odd games in the Atari environment. Okay. So that's led to a sea jump in interest and renewed interest in reinforcement learning, and since then a lot of new algorithms and achievements have been made using reinforcement learning, at least as a component of many realistic settings. Okay, a component in many realistic applications. Thank you.